Welcome to parametric equations. The basic idea here is where and when does something happen. Rectangular equations, oops, I meant to do that one like this, tell you where something happens. But what we're going to look at is parametric equations because those will provide a when and where. When and where. And that's why we start with a T for time, because we'll be figuring out the amount of time something takes or how long to get somewhere. So let's take a look first at graphing a plane curve defined by these parametric equations. They're parametric equations because they use a T for time in them. And here's how we're going to do it. I already set this T up in the first column. We're going to put these equations in here. Okay, so this one is x equals square root of t. And so the first row is the headings. Now let's get that right. First row has the headings for the columns. We're then going to have y equals t minus 1. And at the end, because we're doing an x and a y, we will get an x and a y that we'll be able to plot in order to graph it. So notice, please, that we are limited because the time has to be greater than 0, which makes sense. You can't have a negative time. We don't go back in time unless you're reading a science fiction story. So let us start with 0 for our first time, for our start. So x is equal to the square root of 0, and the square root of 0 is 0. And that same time will be put over here in the y equation, and 0 take away 1 is negative 1. So we have 0 and negative 1. The distance can be, or rather, the y can end up being negative, and even the 0 could if it was set up in a different equation, but the time cannot be. So we have to start with positive numbers here. So let's go to 1. X is equal to the square root of 1, and the square root of 1 is 1. And that same 1, y is equal to, the t is 1, so we're going to put 1 in there, and that comes to 0. So now we have a 1 and a 0 that we'll graph. I'm going to choose to put a 4 next because it's a perfect square, and that makes this easier because then we have a 2. Y is equal to, the time is 4. 4 take away 1 is 3. So we got a 2 from the x and a 3 from the y. And then I'll choose 9, perfect squares to make it easier. This will also make the graphing easier too. For graphing also. So x equals square root of 9, which is 3. Y is equal to 9 minus 1, which is 8. So we get 3 and 8. These points we want to plot. So there's a graph down here to help us with plotting them. Let's do it. 0 and negative 1. 1 and 0. 2 and 3. 3 and 8. Notice it's going only on one side because we can't use the negative x's because they're the negative t's. It only starts with the 0 here. So in this case, it actually works where the x's end up with the same domain as the t does. So what we've done here is set up where that this is going here, but it starts and goes in a certain direction. So we actually have to put directional arrows. For t greater than or equal to 0. And that is then graphed correctly. There's a starting point, and then it continues, but only in that direction. Right? So there's the first example of using parametric equations. Let's go to the next page. We're going to use the exact same problem. However, this time we're going to do something a little different. We're going to eliminate the parameter, which is the t. Same as last, but different method. So what we're going to do here is we're going to take this x equals square root of t, and we're going to square both sides. You're allowed to do that in math. You can do something to one side as long as you do the same thing on the other side. So we get that x squared is equal to t. So what we're doing here, I'm actually going to draw a little line here and write the steps that we're going to do. And the first one is solve for t. The second one is to substitute. So here we have y equals t minus 1. We now know that t is x squared, so we can say y is equal to x squared minus 1. That is our rectangular equation. So we eliminated the parabola, and it gives us a rectangular equation. There's no t in that, but this is now a graphical equation. Well, let's do this to show you that that's like part of our answer there. Now we're going to sketch the curve for it. Okay? And notice this here, that t is greater than or equal to 0. If it doesn't give you that, then you're allowed any t's, negative or positive, because a negative time is not really negative if you're just starting off at a certain point and moving somewhere. So we'll graph that. Let's do a simple XY table. If I put 0 in, I get a negative 1. If I put 1 in there, I get a 0. If I put a 2 in there, 4 minus 1, I get a 3. If I put 3 in there, I get an 8. Those may look pretty similar to something you just saw. So I will graph them over here anyway. Oh, I should put for 3, sketch it, which means graph it. Okay? And so I have those same points. And then no arrows. You have to show the arrows. Now, one of the ways, the general gist, if you're not sure which way to go, think of it as 0 degrees around the unit circle, okay, which generally means like going counterclockwise. So that's one way to think about it. So here's the starting point, then it goes there, and we have just graphed it. And it's actually the same as the last problem, just done differently, because here we were told to eliminate the parameter. And we will do that on the next one, which has some trigonometric equations. So we're still going to follow the same steps. The first step is to solve for t. So here, if I divide both of these by 7, although what I'm really going to do is I'm going to solve for sine of t. Watch what happens, you'll see why. Divide both sides by 7, and we have that the sine of t is equal to x over 7. And on this one, we'll do the same thing. So we get that the cosine of t is equal to y over 7. So, and I'll write it over here. Solve for sine or cosine of t. The next thing we'll do is to square both sides. So that gives me sine squared t equals x squared over 49. And the same thing here. Cosine squared t is y squared over 49. Why do that? Well, we're going to do that because we're going to use the fact that sine squared theta plus cosine squared theta equals 1, the Pythagorean identity in trigonometry. So watch what I do on this next line, because this is going to seem weird at first, but it's very useful because of the fact that one side of an equation equals the same side, the other side of the equation. So these two sides are equal, and what I'm going to do is simply write them as the same thing over again, because that is true, isn't it? Sine squared of an angle plus cosine squared of the same angle is equal to sine squared of that angle plus cosine squared of that angle. Clearly, the two sides are indeed equal. But here's what it lets us do. It lets us take this and put it in here. It lets us take this and put it here. And all of this becomes 1. So sine squared of theta is x squared over 49 plus y squared, oh, not of theta, just x squared over 49. Yep, cosine squared theta is y squared over 49. Now multiply, so actually what I did, this was to substitute. I substituted for sine squared theta and cosine squared theta. Okay. I could have just put 1 at the original beginning part, but still I like to do that. Now we're going to multiply both sides by 49. We get x squared plus y squared is equal to 49. And we have an equation of a circle. That gives us some information. The center of the circle is 0, 0, and the radius is 7. So we can go and graph that using those two pieces of information. I can do this. So I have this info, 0, 0. And if I went to 7 in all directions, I could make a circle. But I'm going to have to pause for a second because I'm only allowed on here to go from 0 to pi. And on the unit circle, for example, 0 to pi means going from here to here to here, but not going past it because that's where pi is. So if I had 2 pi or had no limitation, I could keep going, but I can't. So here's the start of it, and it goes in that direction of 0 towards around the half circle, and it stops there. So there's no arrow at the end. It just goes up to there and stops. And I will yellow that in to show that it's only that. So that's a different type of one. It's a circle, but only part of it can be used. And you find out what the circle is by changing from these, having those parametric equations and changing them into a rectangular equation. And it's from eliminating the parameter. Let's take a look at a practice one. Here we're eliminating the parameter again. We'll write the resulting rectangular equation, then sketch it. All right, let's take a look at what we have. I'm going to do the same steps as the last problem. So cosine of t is here, and I'll divide both sides by 3. Cosine of t is equal to x over 3. Sine of t, dividing both sides by 8, is y over 8. Let's square them. Cosine squared t is equal to x squared over 9. Sine squared t is equal to y squared over 64. Now I'm going to use the Pythagorean identity. sine squared of theta plus, oops, something went black. Okay, we're back. Good. Sine squared theta plus cosine squared theta is equal to 1. And we're going to substitute these, but the sine one's over here. So I'm going to be putting the y squared first. And then the cosine one second. And notice we have the equation of an ellipse. And it's a vertical ellipse. And we know that because the y squared is over the larger number. For an ellipse, that matters. The a is 8, a squared is 64, that's larger than the b squared. Therefore, the y, because it's parallel to the y-axis, where we have a vertical one. Let's do the whole thing here. And now we can graph it. We have enough information with this to be able to graph it. So we know that the center is at 0, 0. We know that A is 8 and that B is 3. That's enough information to do some graphing here, and the fact that it's vertical. Right? So when we put 0, 0, we're going to go up 8 and down 8 because we know it's a vertical ellipse. And 3 and 3. Now let's look and see about what we can use. Over here, it looks like we can use the entire round part, starting at 0, going all the way around as if it was the unit circle, because we have 2 pi at the end of it. So I'm going to draw up to here and continue drawing and continue drawing and continue drawing. Ooh, that's one of my better ones. Good. And then I have to do the directional arrows, and the directional arrows start at 0, 0 and go following the line in that direction. So we have an ellipse, a vertical ellipse showing, and in that direction. Ooh, I didn't want those to disappear. There, now they didn't disappear, they're back, yay. So I eliminate the parameter to get a rectangular equation. This is called rectangular equation. It's not parametric because it doesn't have a t in it for this context here. And we sketched it and put the arrows. Now let's go slightly different here. Let's now make parametric equations. Some of this is really easy. The first two of these, well, the first one's extremely simple. And after that, it's still easy. It's just plugging things in, and you just have to be given the formulas or know the formulas for it, which will be given to you on an exam if necessary for this type of problem. So to make parametric equations for a parabola, one is you simply let x equals t. That right there is one of your equations. Then in the function you're given, you replace x with t in the given equation or function. So first for this one, x equals t, I just did that. And then I'm going to replace this x here with the t, 3 minus 4 t squared, and that right there, that's our answer. Or those are our two answers. So these are the parametric equations that go with that parabola. We'll do the same thing on the other side, and it's just that easy where we just say x equals t, and then put a t in for the x. T squared minus 36. Oh, that went away. I didn't want to. Good, now it's back. All right. Now we get to something slightly different. We're going to go up a little bit harder, and then after that we'll get to where it's not really still that hard, but there's a couple of twists to it. For this one, notice that x is a little formula, and y is a little formula. And this is when we want to make parametric equations from a circle. So we have here a circle, and in that circle, the center is a positive 4 and 6, and the radius is equal to 3. All right, so that's enough information. That's our H, that's our K, and notice we have to have H and R, K and R, and that's really all we need. So this one, X is equal to H is 4, plus the radius of 3, cosine t, and here y is equal to 6 plus 3 sine t. That's all it is. You simply just plug in the 4 and 3 and the 6 and 3. So here you have to know or be given the formulas for it. And on the next one, there'll be a twist, because in a circle, there is no vertical or horizontal that changes it. On the next one, now on page 4, handout here, for an ellipse, you could have an ellipse that's going vertically or horizontally. So you figure that out based upon the fact that whichever x or y is on top of the larger denominator, that then being a squared, the x means we're parallel to the x-axis, so this one is horizontal. And that means we'll use these two equations that are given. They're different from the last equations. Okay, so we need an H and a K just like before, but now we are using A and B for them, for the coefficients, not the R because there's no radius. But A and B is like the radius as it changed one way or the other, sort of. It's a different conversation. If it's vertical, we will switch the A and the B, and we'll do that over in the second problem. Right now, though, we have some information here that helps us on this one. We know that the center is -7 and 2, and we know that A equals 5 and that B equals 3. Well, that's all that we need because of the fact that this is H and that this is K. We can now use those two formulas. So I'm going to do this, and I'm going to write that X equals H plus A cosine t, and then Y equals K plus B sine t. I am just simply using those formulas, those given formulas. But I know what H is, I know what K is, I know what A is, and I know what B is. So I can plug those in. And then I'd be able to use T to get an X if I wanted to. Right now, let's go ahead and write these. X equals -7 plus 5 cosine t. Y equals 2 plus 3 sine t. And that is the answer, or rather, we made parametric equations. These are the two parametric equations. Now, over in the second one, we're going to do the exact same kind of thing, except that now this one is vertical. And we know because it has the y on top of the a squared. Okay, and for an ellipse, a squared is the larger number. Not for hyperbola necessarily, but it is for an ellipse here. So let's get our information out of it. The center, well, that's x with no number, which means it's x minus 0 or plus 0. Y minus the 2 means it's a positive 2 here for the center. And we know that a equals 7, which is the square root of 49, and that b is equal to 4 for that square root of 16. Now, given that, we are going to write the formulas, but this time we're going to switch a and b. So x equals h plus b cosine t. and y equals k plus a sine t. So these changes due to vertical. I'm just going to say vertical because you now understand what that means. And let's go ahead and put in the appropriate numbers because we know the h. Now the h is going to be 0, so I won't even put that. 0 plus something is just that thing. But I'm going to use b, which is 4 cosine t. And y is equal to the k, which is 2, plus 7 sine t. Yeah, that's better for the line. So we have x equals 4 cosine t and y equals 2 plus 7 sine t. Right. So that's an ellipse one, and we used these equations here for it, a little different from the circle equation. Let's take a look next at making a parametric equation for hyperbola. So given the equation of hyperbola, use this one and this one. Notice it has a secant and a tangent this time. So when we switch them, you switch the secant and the tangent, not the A and B, if the hyperbola is vertical. Well, we'll do that for the second problem. The first one here, let's get our information from it. 4 and negative 1. A equals 4. B equals 9. So we're going to simply use those formulas. So in a way, it's sort of easy. It's just plugging in, substituting the appropriate numbers. A plus B tangent of, let's write it correctly, tangent T. So notice it has the secant and the tangent here. So let's plug in each of these numbers because we know what H is and K is. We know what A is and B is because of these things. So X equals 4 plus 4 secant T. Y equals negative 1 for K plus B is 9. So it's 9 tangent T. Do the last one. Notice right now that because the y squared is positive, that makes this vertical. So this one's vertical. So that means we will switch secant and tangent. First, let's get the information we need. The center is negative 5 and positive 3. A is 10, square root of the 100. B is 7, the square root of the 49. And we'll put down these two equations. X equals H plus A, and I'm going to put the tangents this time. And then Y is equal to K plus B secant this time. So those two are switched. Let's put in the numbers. H is negative 5. A is 10. Tangent T. Y is equal to 3 for the K plus 7 secant T. And those are the two equations for the hyperbola. catch up there. So what we've looked at is the basic idea for parametric equations to get a time or a direction in time there. Following this is one method to sketch it, and this eliminating the parameter as a different method to sketch the same thing. And here eliminating parameter for a circle and being limited to only half of it. And in this ellipse, we could use the whole thing, graphing it essentially, but putting those directional arrows. And then changing to parametric equations, which are easy in some cases, and still easy here, where you have these formulas. You just need to be careful of the changes when you go vertically. So there is an application for this, but that will be at a different video, because that one can get pretty involved, and it's be fun to look at. But I'm going to stop here for the first part of this. Hopefully this has been helpful for all of these problems, and thank you for watching and listening.